Okay guys, so up to this point you are familiar with the derivative. You've been differentiating functions, polynomials, trig functions, exponential functions. You've just been having a go at it, and that's really cool. But there was something really interesting about those functions, and they were explicitly functions of a single variable. For instance, x could be theta. Whatever the variable is, think of the variable as being a dummy variable. So if I gave you something like y equal to e to the x, and I asked you to differentiate e to the x, then you'll say something like dy dx is equal to e to the x. Up to this point, y equal to sine theta, dy d theta is cos theta. Okay, so we can actually see the dependence of the variable. So sine is an operator, it operates on that variable theta. The exponential function e operates on x as in e to the x. So it's pretty explicit. We can see clearly the dependence of the operator on the function. But what happens if the function we know is a function of x? For instance, we say something like y is equal to y of x, where the functional dependence is not explicitly given. What happens then? And this is where we call on our ability to differentiate implicitly. Let's take a closer look at that. All right, so simply put, if we take an example like, as I said, y equals to e to the x, no prizes for guessing here, dy dx is e to the x. If I gave you f of theta, let's be fluent in this now, is sine theta, then df d theta is what? It's cos theta. We also know how to use the chain rule beautifully. So for example, I gave you something like y equals to cos of 2x. Differentiate the inside function first. So dy dx, what is d dx of 2x? That's 2, and then the outside function d dx of cos is sine of what? 2x. So we're familiar with this, but here's a situation developing now. If I gave you a function, something like f of x is equal to e to the y, where y is some function of x, what is the derivative? Df dx. That is interesting. That's what we need to look at right now. So let's just go to a very simple one. If you took y equals to x squared, we know that dy dx is 2x. I'm going to give you a function like this. F of x is y squared, where y is some function of x. So for example, if y is equal to x, then f of x is x squared. That's exactly what we have here. Then we know that df dx is 2x. But what if I'm not going to give you this one? I'm not going to tell you explicitly what y is. So how do we differentiate the original function? And this is the heart of this lecture. So let's just take it a step further in the next slide, not to cloud what we have here. So let's go. So f of x is equal to y squared. We know y is a function of x. So watch this, using the chain rule, df dx, not df dy, df dx, surely must be df dy dy dx. Does that make sense? Okay. And if we write this, what is df dy? Df dy is 2y. And when you see a dy dx, just write down y prime, because we don't know explicitly what y is. Okay. Now let's just take what we've just learned here and apply it to this example that we had previously. F of x is y squared, y is equal to x squared. So we know that df dx is df dy dy dx. Df dy is 2y. Dy dx, here, is 2x. So that becomes 2 times 2, that becomes 4xy, like that. But y is x squared, so that becomes, if it's y squared, we substitute y there, that becomes 4x cubed, like this. Okay, so we know that. We actually know that. So if we go back, because this example is really simple, is this actually correct? If f of x is y squared and y is x squared, then df dx is 4x cubed. Because the example is really simple, just do a direct substitution. If f of x is y squared and if y is equal to x squared, it's pretty obvious that f of x is x to the power 4. And we know that df dx from grade 12 is 4x cubed. Have a look. Okay, so when it's not explicit, the functional dependence of y on x, or the variable could be theta, whatever, then you've got to employ what you call implicit differentiation. And what you would find, these y primes start creeping up. It's nothing more than the use of the chain rule, a more elegant form of the chain rule. Okay, so what I want to do, guys, right now is emphasize something that's very, very important. I think most students actually miss this. Let's take a function f of x, right? And that is sine x. So what is f prime of x? We know is cos x. Take a function f of y equals to sine y. So what is f prime of y? F prime of y, remember I'm saying df dy, that is cos y. But have a look at this one. F of x is sine y. Aibo. Now you're saying, where is the x? Well, and we're saying that y is a function of x. We're not going to tell you what function it is. It could be x squared, it could be e to the x, could be whatever. We're saying it's implicit, right? It's a function of x. If I want, watch this, df dx, not y, df dx, this would now become df dy dx. But what is df dy? Df dy is dy of sine y, which is cos y. And I told you, dy dx we write down as y prime. Okay, that's pretty straightforward. Now, let's work backwards. Let's just say for this function over here that y was actually x. Let's make it very simple. So here we're saying that f of x is sine y, where y is equal to x. If y is x, then this is nothing more than sine x. And we know the derivative df dx is cos x. Now, will this that we found here using implicit differentiation also give us cos x? Well, let's just have a look. We say df dx is cos y. What is cos y? Cos y is cos x because y is equal to x. And what is y prime? Well, y prime, remember, is dy dx. So what's the derivative of x? It's 1. So our answer is cos x, which is exactly what we had before. This is not confusing. This is not rocket science. Okay? But you got to be careful. Watch, for example, let's try something like this. I got f of x is equal to y squared. Okay? So what is df dx? Not df dy, df dx. Df dx is df dy dx. Df dy with respect to y is 2y. And dy dx, what do we write that as? Let's get this. It's y prime. So a lot of students are going to write the following, and I'm telling you this now. F of x, nice mangoish color, is y squared, and they're going to go df dx is 2y. That is incorrect. You've got to have the y prime there, and you can see y from the chain rule. y. Let's try something else. G of x is equal to e to the y. What is dg dx equal to? Just as before, it's not explicit. There's no x. I can't see the x explicitly. I can't see it. So if I can't see it, then it's going to be dg dy dx. If I differentiate that with respect to y, that's e to the y. And what I said about this one is right as y prime. Okay, making sense now? Let's try another one. H of x is equal to, give me. Let's give you something like sine y squared. What is dh dx equal to? Well, it's dh dy dx. Haha. But now I've got a y squared. You've got to be careful. So if I differentiate the inside function, what's the derivative of y squared? Well, we know it's 2y. What's the derivative of sine of something? It's cos of that something. And then, don't forget, times y prime. So you notice what's happening here. Every time we differentiate implicitly, we're always having a y prime. Makes sense, because y is not given explicitly as a function of x. Let's try something else. Let's knock ourselves out. This is so much fun. We know that if f of x is equal to ln x, what's the derivative? We know that df dx is 1 over x. We learned this. Pretty straightforward. But what if f of x is equal to ln y? Think about that very carefully. What is df dx equal to? Well, df dx is df dy dx. Makes sense, right? What is df dy? Derivative of ln y with respect to y is 1 over y. dy dx y prime. So beautifully, it's y prime over y. Done. Beautiful. Simple.